Tuning in from the East Coast of the United States at 7 p.m. I've seen a lot of folks on the chat feed from Brazil. Welcome. Glad to have you with us a little bit later in the evening for you. And some folks from the UK and the Netherlands. Good for you because it's getting pretty late over there. Very glad to have all of you with us. It's just about 15 minutes to sunset here in Flagstaff, and we will be able to see Jupiter and Saturn for about the next 2 hours. We've got a couple of telescope feeds running for you, as well as a nice image that we can show you as the live stream progresses. So to start things off, I'd just like to point out we've got a schedule of a number of presentations for you. We love doing live streams like this and talking with everybody about all the cool things that are going on in the sky. But there's also a lot of research that goes on here at Lowell Observatory, and we have several of our astronomers and some of our educators with a variety of different programs about everything associated with the conjunction and what's going on in the sky tonight. And you can find that agenda right below the YouTube window in the comments section, so you know who is talking about what and roughly when. And so we'll be talking about the conjunction itself, both the astronomical side as well as the cultural impacts. You'll hear about Jupiter and Saturn's moons, a little bit about a meteor shower that's going on, and a number of other topics. So thanks again for joining us, and we're looking forward to the next 2.5 hours coming to you live for a pretty historic occasion up there in the sky. So to get things started, one of the interesting things that goes with this conjunction, not only is it an unusually close approach of Jupiter and Saturn, but it happens to fall right on the solstice. So the first day of winter here in the northern hemisphere. If you're watching from the south, of course, you're getting into summer. And the solstices are significant days throughout the year, celestially and in history. And we thought we would start tonight with a little discussion about that, where we are in the celestial year. And to talk to you a little bit about that, we have our Deputy Director for Science and Professional Astronomer, Dr. Michael West. Michael's been with us for about 6 years. His research specialty is in galactic astronomy and the structure and dynamics of galaxies and the large-scale structure of the universe. And so I would like to bring Michael on right now. And while Michael is talking, you will notice on the YouTube feed to my left, on the left side of the YouTube feed, we have an image. The image you saw just before was coming to you live from the Giovanni Open Deck Observatory. And right now, we're switching to an image that we took at the 4-meter Lowell Discovery Telescope just yesterday you can see Jupiter there on the screen. So at this point, I'm going to pass it off for our first presentation of this live stream to talk about what's going on celestially this day in terms of the solstice. And so, Michael, I'll pass it off to you.
Okay, thanks very much, Jeff. Let me just start my presentation. Hello, everyone, wherever you are in the world. As Jeff said, my name is Michael. I'm one of our astronomers here at Lowell Observatory. And I wanted to just talk a little bit about the cultural significance of the solstice. If you're in the northern hemisphere, of course, this is the winter solstice. If you're in the southern hemisphere now, it's not going to be the winter solstice, it's going to be the summer solstice. So here in the north, for example, you may have snow where you are, it's cold. But just to remind people that for those of you who are joining us from the southern hemisphere, you're enjoying the warm days of summer. Today's the first day of summer for you. What I'm going to talk about today is the winter solstice and how it's celebrated in different cultures around the world. One of the things I've always been interested in is other cultures and the role that astronomy has played in them. And so, for example, astronomy is not just the study of the stars and the galaxies and the origin of the universe and the planets. It's also played a very important functional role throughout history by serving as a calendar, for example. The stars and the sun rise and set at different times at different locations of the year, and that's provided a calendar for people. Also, this provides a way for cultural rituals and cultural celebrations. This is something, as you know, during this lockdown, during this pandemic, people miss each other. And so having these opportunities to celebrate with one another is really important in many different cultures. So I just wanted to go through a few of the examples of celebrations around the world. Obviously, I don't have time to do everything. I'm sorry, I apologize if I missed your culture. But there's a few just to give you a highlight of the great diversity of how human beings celebrate the winter solstice. Probably the one that's closest to what we would consider a sort of traditional Christmas celebration today was called Saturnalia in ancient Rome. And Saturnalia was as the name implies, it's a celebration of the god of agriculture, Saturn. And during this period, there were many celebrations, and these took all sorts of hedonistic forms. Gambling was allowed, which was frowned upon throughout most of the year. There was food, there was banquets, there was parties, there was pretty much everything, gift giving, very similar to some of what we celebrate today as part of Christmas. And it eventually stretched out to become a week-long celebration, and that was getting a little out of hand, so they shortened it over time. But that's the example of one way that the ancient Romans celebrated the winter solstice. So again, this is a sort of illustration of how they were engaged in all sorts of partying, basically. Probably one of the best known examples, of course, is Stonehenge. Stonehenge is this ancient stone monument in England. It was built about 5,000 years ago by Stone Age people. It believed to have been a human burial site, but it was also built in such a way that its orientation is aligned with certain features throughout the year, like the winter and the summer solstice, for example. So you get many people go there now on the equinox or on the winter solstice or the summer solstice, because the sun will rise through very specific locations among the stones. So it's a calendar, in a sense, is what Stonehenge is. And of course, it's not the only one. Here's another one in Ireland called Newgrange. It's also about 5,000 years old. In fact, it's slightly older than Stonehenge, probably. And it's the same thing. It was built in such a way that there's a certain passage that on the winter solstice, the sunlight peeks through this very narrow opening. So it served as a calendar for people. And again, people love to go there as well. In fact, it gets so crowded these days that they have a lottery for who gets to attend there. And there are many of these kinds of what are called stone circles around the world. Here's an example on an island off the coast of Scotland. Here's another example in the Gambia in Western Africa. And in some cases, it's not known what these stone circles were used for. Often they were associated with burial sites, but in some cases, there's evidence suggests that they may have been used for astronomical purposes as markers of the rising and setting of the sun on the solstice dates or on other dates throughout the year, like the equinox, for example. Now, everything isn't just ancient. Here's a sort of modern Stonehenge called Stonehenge Aotearoa. Aotearoa is the Maori name for New Zealand. And this is a modern one. It was built in 2005. But it's the same basic idea. It was built in such a way that the rising of the sun on the solstice and on the equinox is marked through certain passages on this object as well. And there are many other modern celebrations as well. One you might not be as familiar with unless you live in Brighton, England, is called the burning of the clocks. And this was created in 1993 to offer people the winter solstice. And the idea is really nice. What they do is people make costumes and paper lanterns, and they walk through the streets of Brighton down to the beach, where they then light these things on fire. They light these paper lanterns on fire. And the paper lanterns are made with the themes of clocks and the passage of time. And so what this celebration shows is the passage of time. The year is behind us. bright days are coming, right? Today's the shortest day of the year, the longest night of the year. And tomorrow the day is going to be a little bit longer, and so on and so on. So it's kind of looking forward to the future. And so what they do is they go down to the beach in Brighton and they light these paper lanterns on fire in a giant bonfire, basically. And they also have fireworks. So it's a very modern kind of celebration of the winter solstice. Many different countries, almost all cultures have one celebration or another about the solstice because it's so important. People needed to know, when are the seasons coming? When is winter arriving? When is winter going to end? When can we start to plant crops? All of those things were essential. And so many different cultures celebrate the winter and the summer solstice. In Iran, for example, there's a celebration called Yalda. It's also celebrated in Afghanistan and in the Kurdistan regions of Iraq and other places as well. And Yalda means the night of birth. And again, it's recognizing the fact that we're through the worst of winter in the sense that we're through the shortest day after today. Tomorrow, the days will get longer. The sun is slowly going to come back more and more strongly. And so that's what Yalda is. It's a gathering of people to spend the longest night of the year together with each other, the longest night in the Northern Hemisphere again. And traditionally what this means is that people eat the last of the summer fruits. So for example, the custom in Iran and elsewhere where they celebrate Yalda is to eat watermelon, for example, and pomegranates and nuts. And these are believed to bring you good health during the winter, to avoid getting sick during the cold months, for example. It's also traditional that people will read poetry, in particular poetry from a 14th century mystic and poet named Hafiz. So as one example of a tradition around the winter solstice in the country. Here in northern Arizona, where the Hopi people have lived for thousands and thousands of years, they also celebrate the winter solstice as well with a festival called Soil. And in this case, the Hopi people believe that now is when the Kachina, the wise elders, come down from the mountains. And these are the messengers between us and the universe, in a sense. And so they celebrate this festival on the winter solstice, and they plan for the coming of the soil. The sun is about to come back. And so, for example, you may have seen things like Kachina dolls. So the Kachina are these messengers, these sort of spirits who come down from the mountains. And the elders will tell stories to the young children to make them familiar and to know about the different Kachinas, the different spirits that are coming down. And they give them dolls so that they will remember and know who these different Kachinas are, who these different spirits are. So that's one of the celebrations that the Hopi people celebrate. In parts of Mexico and Guatemala and Nicaragua, there's something called the Danza de los Bailadores, which is the dance of the flyers. And if you've never seen it, go look for the YouTube video. It's pretty incredible. But a very tall post is constructed, and 5 men climb to the top. One stands up there and plays a drum and flute, and the 4 others, as this whole platform rotates, they slowly descend down to the earth. And the idea is that, again, this is celebrating, in this particular case on the winter solstice, the beginning of the brightening of the days with the sun's slow return. In China, there's a well-known festival called Dongji. It's also similar type festivals are celebrated in Korea and elsewhere. And again, it's also a celebration. The name Dongji means the extreme of winter. It's saying this is the worst it's going to get. This is the shortest day of the year. It's the longest night of the year. It's been celebrated for thousands of years. And again, families gather. That's a common theme in many of these winter solstice celebrations. It's cold. The night is long and dark. Families get together and they celebrate. They have fun. And so that's what's done in China. In this case, as in many festivals, there's often a particular kind of food associated with this. In this case, it's a dish called tangwan. It's made from rice flour, often filled with sweet sesame seeds or with bean paste. And then it's served in a warm, sweet sauce as well. And the idea was that the idea behind this festival comes from the Chinese concept of yin and yang. And in this case, during the dark of the long winter night, energy is low, so you need to eat foods that are high in energy. And so a sweet dessert like this, for example, brings a lot of energy to people. In India, there's a festival called Lodi, and Lodi also is the same idea of a, Sorry, just trying to get my presentation back. There we go. It's also a celebration of the winter solstice. It's primarily celebrated in the north of India, the regions of Punjab. And again, it's when people get together, they get together with family and friends, they exchange gifts, and they also have a bonfire. And again, this is a festival that sort of celebrates the god of fire and gives thanks for a bountiful harvest. And so people will throw small tokens of food that they've harvested into the fire. So it could be peanuts or sesame or corn, all those things. And there's dancing and there's partying, and it's just a nice celebration as well. And as I said, gifts are exchanged also. And then finally, I'll finish up in Africa, for the Zulu people. There's also a celebration, and it was actually outlawed for many years when during the colonial period when the British were there, but it's been revived in recent years, and it's basically called the First Fruits Festival. And the idea here is that as the harvest season comes, it's giving thanks for hopefully a bountiful harvest. And what happens is that the Zulu king gets the first fruits, and then when he deems that they're okay, he makes them available to everyone. And so there's a big celebration on that day as well, and all the people can enjoy the fruits of their harvest. So as I said, these are just a few examples of some of the many ways that cultures around the world celebrate winter solstice. Wherever you are in the world right now, hopefully your culture is doing the same. You may have one tradition or another. Human beings are really amazing, and the diversity of ways that humans find to celebrate seasons like this are really incredible. Another one is in Peru and Bolivia. The descendants of the Aztecs celebrate Inti Raymi, which is another celebration of the sun and the bountiful harvest. And here's a quick video showing you some of that. So this is in Cusco, Peru. So as I said, this is in South America where it's summer now. So this would be the celebration in their winter solstice, which is 6 months from now. Same thing in Chile and Argentina. The Mapuche people, who are the indigenous people of that region, celebrate a very similar festival of the sun. But again, that will be 6 months from now when they celebrate their winter solstice. So let me finish up just by wishing everybody a happy solstice and a great and much better 2021. So thanks, Jeff. Over to you.
Okay, thanks, Michael. Thanks for all that information about the solstice, which clearly is a significant day for people all around the world. Hope you enjoyed that presentation from Michael. I can see we have people from all around the world, about 46,000 of you on the stream right now. Sometimes when we do these live streams, we like to do some Q&A with what's coming in on the chat, but I can assure you it's scrolling by way too fast for us to pick up questions. So we're going to try to cover everything about the conjunction and things associated with it to hopefully cover a wide range of topics and answer your questions anyway as we go along. I will note as the chat's going by, Michael, I noticed one person who said that was really interesting information about all the different cultural celebrations of the solstice, and really appreciated that. There was also one comment that went by quickly on the chat saying that Saturnalia sounds like quite a bit of fun, actually. And so maybe we should actually bring that back. So anyway, So let me update you with where we are right now. What you're looking at on the feed is a live view from the Giovanni Open Deck Observatory here on our campus in Flagstaff, Arizona. It is just about 5:20 p.m. It's just past sunset. And if you've been looking at this live view, you'll see that that bluish background has been getting deeper and deeper blue. The sky is gradually getting a little bit darker. You can see Jupiter right there on the left and Saturn considerably fainter to the right, but you can clearly see the rings projecting out from the disk of Saturn, roughly 11 o'clock to 5 o'clock. Saturn, of course, looks considerably fainter. It's a bit smaller than Jupiter, and of course, it's much farther away, about twice as far away, so it's going to appear considerably fainter. We will be able to observe the planets here as the sky gradually gets darker for about the next 2 hours, maybe a little less before they set. And remember, this is an ongoing event. You know, if you want to take a break from the live stream and just walk outside and look, here's where the planets are. This is unfolding slowly. Today is the closest approach, but it takes a while for this conjunction to play out. And we're going to talk about that in just a minute in the next segment on the show. And now I'll ask if we could switch. We do have some talent behind the scenes. Sarah Bircher, our outreach manager, is running things for you up at the Giovanni Open Deck Observatory. And Danielle Adams and Heather Craig from our communications department are doing all the technical wizardry to make this feed work. And they have just switched now to, this is a static image that we took yesterday at the Lowell Discovery Telescope. You can see that at the top, the 4.3 meter Lowell Discovery Telescope. So 4.3 meters refers to the aperture, the diameter of the primary mirror. This is our flagship research telescope. I mentioned at the start of the stream that a central component of our mission is astronomical research and discovery. We have a faculty of 14 professional astronomers, postdocs, graduate students working with them, doing research in all areas of astronomy, several of them, such as Dr. Wester here with us tonight. Telescopes are the tools of the trade, and the Lowell Discovery Telescope is our flagship with a mirror 14 feet across. And in fact, they only used half the mirror to take this. They wanted to make sure we didn't get sunlight onto the optics of the telescope. And there you can clearly see Jupiter at the bottom, showing some detail with its cloud belts. And the Galilean satellites, one out to the left, 3 to the right, and then Saturn up at the top with its rings clearly visible. And this is a really good look at Saturn. The rings are tilted right now, so you can see them clearly. Sometimes they're more edge on, what we call a ring plane crossing, and that's a lot harder to see. So anyway. So there's a question that's come in the chat that I think we're going to cover in the very next part of our show. And that question is, are the planets actually going to come together like an eclipse? And I think that's a perfect segue into the next section. We're going to have both one of our educators as well as one of our astronomers to talk to you about just that. So at this point, as it slowly starts to merge into twilight here in Flagstaff anyway, I'm going to pass it over to Jose Schindler. Jose is one of our outstanding educators. When we can reopen after the virus settles down, if you come visit us, Jose is one of the excellent people who's up there showing you views of the sky and everything like that. And she's going to give an overview of the conjunction itself and what's going on in the sky tonight, so you will have sort of an idea of what you're seeing when you go outside a little bit later or in the upcoming nights and look at what's up there. So Jose, take it away.
Yeah, hi, thank you, Jeff. So I am going to talk a little bit about the kind of the mechanics of how this conjunction works. So we can go ahead and just get started with that. So yeah, just repeat, I'm one of the educators at Lowell Observatory. I've been here for about 5 years now. It's a great place. And yeah, so the very first thing that I want to talk about is where to look in the sky and how you can see this. So I've already seen like a lot of people have been asking about when they're going to be able to see this, how to view it, and it's going to be pretty easy. Anybody can go outside right now. Well, maybe not right now if it's already way past dark for you. But here in Flagstaff, it's just after sunset. The sunset right about now or so. And for the next hour or so, I'm going to be able to see Jupiter and Saturn pretty easily in the sky. So where you're supposed to look is go outside at sunset your time, wherever you're at, and you can look in the southwest sky. And you're going to see what appears to be a bright star. And that bright star is right here. And it looks like one bright star, but as it turns out, it's actually Jupiter and Saturn. And they're so close to each other, they just appear as one bright star together. So it's in the very low southwestern sky. You're going to find it about 10 to 15 to 20 degrees up above the horizon. That's going to be not much more than the width of your fist at arm's length. So you'll see it right after sunset until it sets below the horizon. I know here in Flagstaff, we have trees that get in the way, and so we lose it a lot earlier than people in other areas might be able to. Now, what you're going to probably be interested in is how can you actually see this, right? We can see this with the naked eye. People have noticed these great conjunctions for thousands and thousands of years now. People paid attention to this, but without binoculars or without a telescope, it will appear as just one single star in the sky. And this is not something that is going to happen instantaneously and then be gone. You're going to see this happen over the course of several weeks and several months. You're going to see them getting closer together. And today just happens to be the day where they are the closest that they're going to be for now. So if you do have a pair of binoculars at home, or if you have a telescope, I skipped that whole part, that's fine. If you have binoculars at home or a telescope, you'll be able to get an up-close view. So I have this little video here that's going to show over the course of the month of December, pretty much, how these planets have gotten closer together over time. So I'm going to play that real quick, and you can see they're trailing down in the southwest sky in this picture here. And you're going to be able to view this conjunction all the way up until probably mid-January. And then by January, they're going to be too close to the sun and you won't be able to see them anymore without hurting your eyes. So pretty much after sunset, between now and the end of the year, you can go outside, look in the southwestern sky, and you're going to see Jupiter and Saturn. And today is when they're the closest, but you'll see they are very close to each other for quite a while. Now, if you do have binoculars or a telescope, you'll actually get to be able to get an up-close view of these planets. With a pair of binoculars, you'll be able to see both of them pretty easily. You'll even be able to pick out the moons of Jupiter and of Saturn. This is a screen grab of just what they are at 6 p.m. my time right now. And you'll see that there's a few moons that are in view. Jupiter has 4 moons that you can see with a binocular, but one of them looks like it's behind Jupiter in this particular image. And then Saturn has up to 4 or 5 moons that you can view with a pair of binoculars as well. And of course, with a telescope, you'll even start to be able to pick out some of the detail of Jupiter and Saturn on their surfaces, like the Jupiter's bands. If its spot is pointed towards the Earth, you might be able to see the great spot. And of course, Saturn's infamous rings. So if you have binoculars or a telescope, you're sure to get a pretty spectacular view. And as time goes by, as they start to get farther away, it'll be more and more difficult to see it with a large telescope, but you'll be able to see these with a pair of binoculars for the next couple of weeks, for at least another 2 weeks. Now, today was their closest approach to each other, so that means that they were as close as they're going to be for quite a while, and their distance from each other in the sky is going to be about 1/10 of a degree. And for reference, The moon is about a half a degree across, and that's about the same width of your pinky when stretched out at arm length. So that gives you like a good idea of how big things appear in the sky for us. And then here's just a reference of what they look like when they're together. So in the image that we have up on the screen from the LDT, those are just about 1/10 of a degree right now. And you can see the size comparison between them. So, so what is a great conjunction? So the technical definition is when the planets, two planets, any planets, are going to occupy the same right ascension or ecliptic longitude. And I feel like that's a whole extra 15-minute presentation. So basically, those are going to be when they occupy the same coordinates in the sky. You're going to see two planets are going to be very close to each other. It's going to be the closest that they are for some time. And you're going to see them get closer together, and then they're going to get farther apart. And then when they're the closest, that's the conjunction. And for Jupiter and Saturn, we call it a great conjunction when they are the closest to each other, mostly because Jupiter and Saturn are really great big planets and they're exciting conjunctions that can happen. So the reason that these happen is Jupiter and Saturn, as they go around the sun, they are going at different speeds. Jupiter orbits the sun at about 12. It takes 12 years for the Jupiter to orbit the sun once. And it takes about 29 years for Saturn to orbit the sun once. So that means Jupiter is going about twice as fast as Saturn. Now, when these conjunctions happen, they are not going to collide with each other because Jupiter is also about half the distance to the sun as Saturn. Saturn's twice as far away. So while they look like they're colliding with each other in the sky when we're watching it with the naked eye, in reality, they're much farther away from each other than it seems. So it's just a matter of perspective at this point. So yeah, what happens with this great conjunction, Jupiter going much faster than Saturn in the sky, is passing Saturn up in its orbit. And it's going to start making a new orbit around the sun pretty much. And it turns out Jupiter will pass Saturn by about every 20 years or so, or 19.8 years. So every 20 years, we get another great conjunction. And now this great conjunction is particularly special because of how close it is. The last great conjunction happened in the year 2000, the day after my birthday, actually. And it was what one would probably consider not a very good conjunction. Their distance apart was more than a degree, so twice your pinky finger. And it also happened very close to the sun. So it happened in the daytime and nobody got to view it. So the one that happened in 2000 was not considered a very exciting conjunction. The last time that Jupiter and Saturn were as close in the sky as they are today was 400 years ago. In the year 1623, they were a little bit closer than they are now, right? They were about 0.08 degrees, less than a tenth. But that one also happened in the daytime. It was too close to the sun, so people didn't get to see that one then either. The last time that anyone watched a great conjunction that was as good as the one that's happening tonight was 400 years before that in the year 1226. And those were incredibly close to each other. They were about a third of the distance apart than what they are today. So even closer, which is hard for me to imagine. And this one was viewable in the morning at that time. So they didn't have telescopes, so they couldn't get up close views. But like I said, you don't need a telescope to be able to view a great conjunction. So people watched it, I'm sure. And there's an image that I have right here of what the sky looked like on March 4th, 1226. You can tell it was during the summertime because some of the summer constellations are up. This was actually a pretty good sky because it also had Mars up high and we also had Venus close by. So 4 of the 5 visible planets were able to be seen at that time, which we don't usually get that very often. Now, there's some good conjunctions that are coming up in, when I say the nearest future, I mean the far distant future. The next great conjunction that is going to be as good as this one tonight will happen in the year 2080. So we will find great conjunctions in 2040 and 2060, but they will be pretty far apart. They'll both probably be a little bit more than a degree apart each. And this one will be viewable in the morning. And this one's exciting because it could happen while some of us are still alive. This is not too far in the future. So maybe when I wake up and I'll be like really old and I'm going to go out and I'm going to watch the conjunction early in the morning. And they'll be about they'll be about 1/10 of a degree apart then as well. So a similar view to what we have tonight. Now, after that, the next good viewable great conjunction where they're close together is again in about 400 years. It's going to be in the year 2417, and they're going to be just a little bit less than 1/10 of a degree apart, which is much closer than what they are today. So I don't plan on living that long, but some of you all might. So I'm sure it'll look really good. And then after that, some more interesting ones that we might find one in the year 7541. So 5,000 years in the future, they're actually going to transit. Jupiter is going to pass in front of Saturn partially. So you will see Saturn partially obscured by Jupiter as it passes by. Now, of course, this is so far in the future that the data might be a little bit off from what we have today, but I don't think any of us are going to live that long to see that. So it's okay if it's a little off. That same year, we're going to have another great conjunction of Jupiter and Saturn, and this time, Jupiter will completely obscure Saturn. It's going to cause what we call an occultation. And this is the first occultation of Jupiter and Saturn since about 7000 BC. So this is about 13,000 years in the making right here. These are very, very rare occurrences, and I'm kind of sad I don't get to see it. However, these, as you can see, these are not very common, especially these occultation. I know that someone in the chat did ask if this was going to look like an eclipse, and the one that happens today, they're not going to pass in front of each other. We're not that lucky. It's the year 2020, guys. And then why does this happen? Why is this so rare? Well, as it turns out, it's because Jupiter and Saturn's orbits aren't on the exact same path. What you can see in this picture is you see the sky with a bunch of lines on it, and there's a yellow line, and that yellow line represents the sun's path in the sky. So that's the path the sun will take over the course of the day. And these red lines, these are all of the planets, and you can see they don't match up perfectly. All of the planets are inclined slightly, which means that sometimes they're going to be far apart from each other in the sky. Some might appear higher up and some might appear lower down, just depending on where it is in its orbit. And so this is why we don't have great conjunctions where they're the same distance every single time. And why it varies is because our planets, they do vary in height above the ecliptic. Jupiter's orbital inclination is about 1 degree and Saturn's is about 2.5 degrees off of the ecliptic. But this also means that if we take the difference between these two numbers, that's going to be the farthest apart that we'll ever see Jupiter and Saturn during a conjunction, which is about 1.5 degrees or so. You guys, 1.2 or so degrees. So you won't see them farther apart than that during their conjunctions. And the farthest apart they were at was actually happened in the 1981 was the last time they were that far apart from each other during a conjunction. So that is the end of my presentation. So I'm going to go ahead and send this back to Jeff again. And I want to thank everyone for listening to me.
Okay, thanks a lot, Jose. And we'll have Jose back a little later in the show just for a recap. One thing we know with these live streams, People are dropping in and dropping out the whole time, so we're going to sort of go back over things a couple of times as we go through the show just to make sure everybody gets the same information. And I'll just remind everybody, in case you just joined, maybe in the middle of Joseph's talk, what you heard there were, I saw a question in the chat. Do we need a telescope to see this? And Joseph addressed that. You do not. The Jupiter and Saturn are clearly visible without any optical aid at all. You don't have to go out and look tonight. I understand from the chat, it looks like it's not a very nice night for observing in Pittsburgh. Sorry to hear that. New England doesn't sound very good either. It's beautiful. I saw someone check in from Cordes Lakes, Arizona. Hello, you're just down I-17 a little ways. It's a beautiful night here, as you can see from our live view here. If you can't observe it tonight, you can go out over the next couple of weeks. Saturn and Jupiter will be drawing slowly further apart. Tonight is the closest approach, but still a pretty impressive sight. And if you go out shortly after sunset, you don't have to be in Arizona or any particular place or another. Within the couple hours after sunset in dusk right over there in the southwestern sky, two very bright but fairly distinct seeming stars, actually the planets Jupiter and Saturn, very closely in conjunction. And frankly, I don't know, as Joe's pointed out, there will be another one of these. These conjunctions happen every 20 years. It's much less frequent that they're really close. So 75-41 for a next really close one. And I don't know. I would suggest let's keep up a really healthy diet and a good exercise regimen, and maybe we can all get back online in 75-41 and really enjoy that one. With that, let me go back over to the feed right now. So what you can see, if you've been watching for the last half hour, right now we're looking at an image from the 4.3 meter Lowell Discovery Telescope. I actually got an email from one of the members of the Lowell Advisory Board, hello Leo, asking if we could have an image from the Lowell Discovery Telescope. Ask and ye shall receive. Here it is. You can see Jupiter down there at the bottom with its cloud belts clearly visible, and the Galilean satellites in a slightly inclined plane there. And then up at the top, Saturn. And our astronomers, Stephen Levine and Amanda Bosch, got that image yesterday with a telescope with a 14-foot mirror, and actually only using about half the mirror to get that image, because we didn't want sunlight to be falling on it. And now if we could go back to our live image from the Giovanni Open Deck Observatory. I'll wait just a minute. There we are. So if you've been watching the stream for the last half hour, this live view, you've seen the background behind the two planets. It was sort of blue, and now it's pretty much faded to black. And indeed, I can see now at 5:43 p.m. here in Flagstaff. We are 7 hours behind Greenwich Mean Time here in Arizona. A little bit of twilight left in the western sky out my window here, so that's now looking pretty dark. And it looks like our outreach manager, Sarah Bircher, has this optimized so you can see Saturn. You can see Jupiter looks a little washed out. Saturn is looking beautiful there and showing its kind of characteristic yellow color. And now Sarah has changed the exposure a little bit, and she's kind of going back and forth there. Since Jupiter and Saturn have very different brightnesses in the sky, we can't in real time bring them out perfectly in the same image. You have to sort of process the image a little bit. So what Sarah's doing right now is going back and forth so you can see different things. Now here, this is way overexposed on the planets, but now you can see the Galilean satellites because they're even fainter than the planets. For those of you who are into astronomical parlance, Jupiter and Saturn are around -1 and 0 magnitude. The Galilean satellites are more like down around 5. They're pretty hard to see, but you can see 3 of them right there. But to see those little moons, the planets are completely washed out. So what we're going to be doing over the rest of the stream, all the presentations will be appearing here on the right side of the YouTube screen. And then over on the left, we'll show you this ongoing live view. So this is a live image of the Great Conjunction. Jupiter and Saturn, of course, are moving, but they're so far away, you won't see motion in real time on the screen. No, I think it's kind of neat there that Sarah changed the exposure so you could see the moons. So Jupiter has these 4 large satellites. Saturn has a couple of really big ones, but they've got this incredible large fleet of moons around them. Easily the largest moon systems of any planets in the solar system. And it just so happens that here at Lowell Observatory, we have a planetary scientist who is an expert on icy moons of the outer solar system. And the planets are kind of getting all the attention, but we thought we really should give a nod to the poor little moons that didn't get ignored during all of this. But they're incredibly interesting objects. And Dr. Jennifer Hanley is with us here tonight, and she is an expert on all things about these moons. And she's going to talk to you a little bit about that. So I'll pass it off to Jennifer.
Thanks, Jeff. Happy to be here. So I'm going to talk a little bit about the moons of Jupiter and Saturn. Here you can see these are the 4 largest Galilean satellites here with Jupiter. And then we just saw in the live stream that you could actually see these with just a low-powered telescope or binoculars. And then here is a collection of some of the moons of Saturn, the largest being Titan. And again, with a slightly better telescope, sometimes you can even see Titan. So I wanted to just start with a couple images that show the scale of these different planets and their moons. So on the top here, we have the sun and the 8 planets here, of course, Jupiter and Saturn being the 2 largest. And here you can see Earth in relative size. And then on the bottom, we have the rocky planets and moons. So again, we have Earth here, and you can see that Ganymede, which is the largest natural satellite in our solar system, is only just slightly smaller than Mars. And then both Ganymede and Titan are even larger than Mercury. And then we have Callisto, Io, and Europa, which are the other moons of Jupiter that I'll be discussing a little bit. Europa is about the same size as our own moon. So here's a really nice video. It's actually a collection of photos that are taken by the Juno spacecraft as it was approaching Jupiter. So you can see here how the moons, the 4 largest moons, are actually orbiting Jupiter as we are, as the NASA mission is approaching to get into orbit. We have another image here showing Cassini. This is taken from Cassini, which eventually was orbiting Saturn, but it flew by Jupiter and took these really cool images. Here you see Jupiter's great red spot, and then the 2 closest moons, Io and Europa, as they happen to be orbiting Jupiter. So we have the 4 Galilean satellites here, Io, Europa, Ganymede, and Callisto. And they all orbit Jupiter in a resonance. So Io orbits 2 times for every 1 time that Europa does, and Ganymede does for every once for every 4 times that Io does. And so you can see here as it's going around in circles, and when it becomes highlighted, that's when they are all in line with each other and being pulled by the tidal forces. And these tides provide a lot of friction on the interiors of these planetary bodies, and it creates energy. So Io is actually the most volcanically active body in our solar system, and it's so active and it's so hot that you can actually see these volcanoes from Earth. One of my favorite images here, it was taken by New Horizons, another NASA mission that flew by Jupiter on its way to the outer solar system. That's very common. A lot of the missions use Jupiter as a gravity assist. And so here we see Tavashtar volcano as it's erupting in a sequence of images as New Horizons is flying by. So Ganymede and Callisto, those are the 3rd and 4th moons from Jupiter. Ganymede is the largest moon in our solar system. They both have a subsurface liquid water ocean below their rocky and icy exterior. But the one that I really want to talk about that I find most interesting is Europa. So here you can see this is an image taken from Galileo. It is, you can see here that Europa is a lot of water ice, but there's also these reddish materials, and that's possibly due to irradiated salts. So if we zoom in on some of the white parts of it, we see lots of really interesting geology. We see these lines that cut across the surface. We see these blocky parts of it here. If we zoom in even further, you can see this is called the chaos terrain. And basically, it kind of looks like a puzzle that might have gotten broken up. And these chaos regions, you can see the different lines here, almost looks like icebergs floating in an ocean, and then it got refroze. And so we see a lot of evidence that Europa's surface is very young. In fact, we even see evidence of plumes or geysers from Europa. And so all this evidence points to a very young surface and a subsurface ocean beneath the ice crust. And salts are really important for understanding the stability and the habitability of that liquid water. So if you look at a cartoon that shows what Europa, the structure looks like, we have the ice crust on the surface, that subsurface, liquid water ocean, and the rocky mantle. And it's possible that there are hydrothermal vents at the bottom of Europa's ocean, similar to how we have these at depth in Earth's oceans. And so there's a lot of energy here, as I mentioned, from the tidal heating of Jupiter. And Europa is probably one of the best places in the solar system to look for life outside of our own planet. So some of the research that I've been working on is to observe Europa with the Lowell Discovery Telescope using different spectrometers. So looking in the visible and near infrared wavelengths to try and identify what salts are present on the surface, and that'll help tell us what salts are in the subsurface ocean and how habitable that ocean is. This is all preparing for NASA's Europa Clipper mission, which will be launching in 2024. And that'll be really exciting. We'll see lots going on here. So moving on to Saturn and its moons. Here we have a cartoon of the Cassini-Huygens mission that orbited Saturn for a long time. One of the big discoveries from Cassini was one of these moons called Enceladus. So Enceladus is a very, very icy moon. It is almost entirely pure water ice. In fact, it's just pure water ice. It's so reflective. It's almost 98% reflective of the sun. If you had it in the sky next to our moon is only about 35% reflective, and this is 99% reflective. And so it would look almost as bright as the sun because it's reflecting all that sunlight. So Enceladus is a very, very interesting moon. You see here these like bluish regions, these lines down here, those are called tiger stripes. And when Cassini flew by really close to Enceladus, it actually saw plumes coming out of these cracks in the surface. And so this is spewing water ice and water vapor out into the solar system. It's actually contributing to Saturn's E-ring. Here's a cartoon of what that might look like in the interior. So we have this rocky material in the middle here. We have a subsurface liquid water ocean again with some maybe heat plumes coming again from the tidal heating of Saturn. And then you can see these cracks in the ice crust and plumes coming out. So again, this is one of the really interesting moons for astrobiology. And then lastly, I wanted to talk about the largest moon of Saturn, that's Titan. Here you can see an image that was taken by Voyager 2, and here's one taken by Cassini a few decades later. And you can see that from the naked eye, it looks very hazy. And that's because a lot of these hydrocarbons or methane haze is in the atmosphere and you can't see through down to the surface. So we sent a probe called Huygens to land on the surface. So you can see here, this top image is showing the atmosphere, and as it gets closer and closer to land on the surface, the image here on the right is from the surface of Titan. And we can see that there's lots of cobbles. These small rocks are about 5 inches, 8 centimeters in diameter. And it kind of looks like it landed in a floodplain. And the really interesting thing is it's not liquid water on the surface of Titan, it's actually liquid methane. So Cassini has a couple of other wavelengths that they can use to peer through that haze and see the surface. So here on the left is an infrared image. We can see the lakes, the darker regions here. And then on the right is a radar image. And so we can peer through the haze and see the surface with the other wavelengths. Now, Titan is really interesting because it is the only other planetary body in our solar system that has liquids on the surface. But whereas Earth is, ranges from 0 to 100 degrees Fahrenheit, Titan is very, very cold. It's minus 300 degrees. And so it's 90 to 95 degrees Kelvin, and the liquid is methane and ethane. So stuff that would be a gas here on Earth is actually a liquid on Titan. I also just wanted to mention that Titan also has a 1.5 bar nitrogen atmosphere. Earth also has a nitrogen atmosphere. Our atmosphere is about 1 bar at sea level. So that's similar, but it's much colder there. And so we have this methane cycle. So methane behaves very similar on Titan as water does on Earth. So you have these methane lakes, they evaporate, you get methane clouds, and then it rains. And so you actually get this whole cycle similar to how water behaves on Earth. And this is going to be really interesting because NASA is sending another mission to Titan called Dragonfly, and it is a dual quadcopter. So it'll land on the surface. This is going to land in the equatorial regions in the dunes to understand what happens when the methane breaks down in the atmosphere and understand what the water ice is doing on the surface. And so it's actually going to fly from landing position to landing position and take measurements once it's landed. And this is launching in 2027, arriving in 2036. So in the meantime, I have been using the Astrophysical Materials Laboratory at Northern Arizona University here in Flagstaff to replicate the conditions that we see on Titan and actually look at the liquid methane and ethane and try and understand what is happening in these lakes. So here you can see is a picture of our lab. And this is a schematic of the sample holder, and we can get down to 30 Kelvin. That's very, very cold. And that's how we can actually recreate these conditions. And so on the top here, you can see some pictures of our samples. And I just wanted to show a little bit about the methane and ethane. If we mix them together and we cool the temperature, you can start to get different types of ice crystals. So here we have ethane ice forming on the left in an ethane-rich solution, and methane ice forming on the right here in a methane-rich solution. And just to finish with one last animation here, this is what happens in a nitrogen atmosphere as we start to cool down. And so you can start to see the ethane ice is forming here. And as we get to really, really cold temperatures, colder than what would happen on Titan, but so we kind of do this fundamental research to really understand the conditions so we can apply it. You can see that the ice completely covers the cell eventually. So yeah, with that, I will end on this image here showing again just some of the moons of Jupiter and Saturn. And again, you can actually see some of these Galilean satellites with the telescopes here at Lowell and even with some binoculars at home.
Okay, thanks a lot, Jennifer, for really interesting talk. It's always interesting hearing about these incredibly neat satellites around these giant planets. And I think one of the coolest things I've seen is one of our telescopes up here at the Gio Valley Open Deck Observatory. You know, there was one night where we must have seen 5 or 6 of the satellites around Saturn, and you could just see the whole system. And I'm really glad you brought up Dragonfly, because you know, the fact that we're now in an era where we are going to be able to fly a drone around the atmosphere of a little moon almost 1 billion miles away. I mean, there's a lot of bad news in 2020, but how cool is it, and how lucky are we to live at a time when our technology lets us do this kind of exploration?
Absolutely. I'm so excited for it.
Yep. Okay. Well, thanks a whole lot. We did actually, one question floated by the chat a little while ago, and actually it was a comparative question between Jupiter and Saturn, asking if Jupiter's gravity has any impact on the rings of Saturn. And I'll just let you maybe answer that one.
Sure. So Jupiter's gravity does not have any effect on the rings of Saturn. They are actually very far apart in space. They just look very close together in the sky because of the apparent, the way they look together. So Jupiter's gravity does affect all of the other planets because it is the biggest planet in our solar system, but it wouldn't affect the rings of Saturn.
Right. Okay, thanks. And in fact, I guess when we see all this magnificent, complicated structure we see in Saturn's rings, that's its own gravity plus all the little tugs from the moons pulling these neat features into the rings.
Yeah, there's some really, really cool pictures that Cassini took of these tiny, they're called shepherd moons. And so they're these tiny little moons, and they go along the inside or outside of the rings of Saturn, and they actually shepherd the ring particles into a really nice shape. It's really cool. I encourage people to go look those up.
Yeah, and they're right on the web. You know, it's NASA imagery. It's out there. It's public domain for you to enjoy and for all of us to learn from. Okay, thanks a lot, Jennifer. Great talk.
Thank you.
Okay, so now we will continue. I'll give you a quick update on where we stand and just a few recaps from some of the earlier presentations. What you are seeing right now on the left side of the screen, again, this is our live view. I did see a question go flying by in the chat. Are these actual pictures? And yes, it is. This is right here live from the Gio Valley Open Deck Observatory. If you look carefully, you can see Jupiter at the left, Saturn on the right, jumping around a little bit. This is atmospheric turbulence starting to get into the picture because they're getting very low in the western sky now. In fact, we're only going to be able to observe them from the Gio Valley Open Deck Observatory for about another 15 to 20 minutes before they start to get into the trees. We do have a second telescope, though, set up to provide live views that's just starting to come in from out at the Lowell Discovery Telescope. It's not the LDT itself. There it is. Live view from the Lowell Discovery Telescope. This is our electrical engineer, Mike Collins, has a 5-inch refracting telescope set up out there. And there you can see Jupiter down at the bottom, Saturn up at the top. Again, jumping around a little bit because we're looking through fairly low in the west and through a lot of atmosphere. But these are indeed live pictures. And to recap a few things I've seen go by, you don't need a telescope, provided it's a couple hours after sunset. So if you are in the Western United States, if you're in California, I just saw somebody say, I saw it with my own eyes in Phoenix, meaning you can see this because Phoenix is not the absolute darkest of skies, about 120 miles down the road from us here in Flagstaff. One question, are the planets actually going to meet? And we addressed that in the previous segment, but I know that people are coming in and out of the feed. They're not actually going to come together and eclipse one another. That will happen in the year 7541. So as noted, watch our website and we'll do a live stream for that one in 5,500 years or so. Let's see. It's great to see everybody from all over the world. Unfortunately, it appears, and I was absolutely shocked to see the comment that it's raining in Seattle. And I love visiting Seattle. It's a lovely city to visit, but I don't have a lot of trouble believing it's raining there. A little later in the show, you're going to hear from our astronomer, Dr. Joe Lama, who's a native of the UK. Apparently, it's cloudy there too. Again, perhaps not shocking, but I'll say hi to everybody from Brazil and Sierra Vista and Colombia tuning in. It's great to have so many of you from around the world. So we actually, so this live view we're showing you right now is from near the Lowell Discovery Telescope. We also have an image that we took with the Lowell Discovery Telescope. Maybe we can switch to that one very quickly. There it is. So we took this yesterday. So this is an image of Jupiter and Saturn by our astronomers Stephen Levine and Amanda Bosch. You can see Jupiter there at the bottom, showing the cloud belts in its atmosphere pretty clearly. It looks like 3 of the Galilean satellites there, one way out to the left. That's probably Callisto, given how far it is, and then 2 in closer on the right, and then Saturn up at the top. And this is a really nice view we're getting of Saturn, because the rings are oblique to us, and they're not always that way. So depending on where Saturn is in its orbit, our line of sight to the ring plane changes. And if the rings are edge on, they're very thin and can be really hard to see during what we call the ring plane crossings, which are very interesting astronomical events for a number of other reasons. But this is, you can see there a really nice view of Saturn's rings. And again, if we were to plunk the moon into this image, it would fill the entire screen, because Jupiter and Saturn tonight are only about 1/5 the diameter of the full moon apart. One more time, if it's cloudy tonight where you are, don't panic. You can go out and see it tomorrow, the next night, as Joe Schindler pointed out in her presentation, for the next 2 to 3 weeks before Jupiter and Saturn start to be a little bit too close to the sun to see safely. So there's still plenty of time. Tonight just happens to be when they make their closest approach before they slowly start to draw apart again. So to say a little more about conjunctions in general and the circumstances and geometry of conjunctions, this isn't the only one. This just happens to be a fairly close one. We have with us tonight our astronomer, Dr. Larry Wasserman, who is also an expert on planetary dynamics, occultations of one object by another. He's spent a career doing this, and he's joined us tonight to talk a little bit about the circumstances of this and other conjunctions. So Larry, over to you.
Thank you. I see we got a question that got posted. Somebody looking in the northwest and the north-south, and it's in the southwest. So that's where you want to look. Okay, conjunctions. There's a formal astronomical definition for conjunctions, which is that they're when the 2 objects that conjunct, that's not a word, are at the same astronomical longitude, called right ascension. But you can be casual about it and say that a conjunction is basically when any 2 or more planets appear in the same general region of the sky. Why is this one a great conjunction? Because it's the 2 brightest, well, they're not the brightest, but the 2 largest planets that are visible to the naked eye, and it's infrequent. So you have the coming together of the 2 planets infrequently, so it's a great conjunction. There are conjunctions that come together even less frequently. Uranus and Neptune will conjunct, there's that term again, about every 170 years. So that's very infrequently, but nobody in the ancient world knew about it because they didn't know about it and they're too faint to be visible. So a little tidbit there. Let me share my screen here for a minute. Okay. Share. Okay, this is a video that our communications department made up, if I can get it to do its thing. Okay, so the planets are going to move. And as we get around here, you can see what's happening. From the point of view of the Earth, the 2 planets are near each other in the sky, and the sun is over here, and that's why they appear near the sun in the sky. There's something else I want to mention for something that's coming up. Let me start it again. Okay, right here, as the Earth comes around, it's moving mostly this way, Jupiter and Saturn are moving this way. And from our perspective on the Earth, Jupiter and Saturn appear to move to the left in the image. But as the Earth comes further around here, in fact, hang on, let me come back again. I have to restart this thing each time. Okay, let's try it again. Oh, that's the other video, which shows, let me go back to the first. Sorry about that. I'm getting impossible here. Let's try this again. From current slide, start. Okay, I think I lost it again. Yeah, this is the second video, which shows that Jupiter and Saturn are, although they look the same distance in the sky, are actually almost 500 million miles apart. And I will describe the first one since I can't seem to stop it in the right place. As the Earth and the Sun and the planets are in a line, the Earth overtakes both Jupiter and Saturn and goes past them. And our view of them is much like the view when you're on a train and you're passing another train next to you. It looks like the other train is going backwards. And at that time of the part of the orbit, it looks like from the Earth that Jupiter and Saturn are moving backwards to their normal motion in the sky. And then as the Earth goes further around, they reverse again and they go back to their normal motion, which is to the east. That'll come into some importance later. Okay, that's all I wanted to show in the way of movies. Well, the question is then, how far apart in time are these events? And how do you compute them? Well, you can't do it in closed form. There's no mathematics you can write down with equations to say how often these events occur, because for several reasons. One, Jupiter and Saturn are moving in ellipses about the sun, and the speed of a planet in an ellipse varies with time. So they vary in how fast they move. Second, as I showed in that movie, we're viewing it on a moving Earth. So that complicates things too. And the third complication is we discussed earlier something about whether or not Saturn's rings are affected by Jupiter's gravity. The rings aren't, but all the planets pull on each other, and the orbits of the planets themselves change over long periods of time because all the other planets are pulling on them. And if you're doing accurate positions of the planets, you need to take all that into account. So we can't do this in closed form, but we can do something that a scientists like to call back of an envelope calculation. Given a complicated problem, can you simplify it enough so you could scribble it on the back of an envelope and get a reasonable answer? And in this case, you can. First, let's assume that the planets move in circles. That simplifies things. They're not very far off because the planets are elliptical, but not very elliptical. Second, the Earth is moving, and that really complicates things. Let's assume we're not observing this from the Earth, but we're going to observe it from the sun, which for a planet that's moving in a circle is right at the center of the circle. Okay, well, how fast does Jupiter move? Well, it travels 360 degrees around its orbit in 11.86 years. So it moves 360 over 11.86 degrees per year. Saturn moves the same 360 degrees around its orbit in 29.46 years. So we know how fast Saturn moves, 360 degrees in 29.46 years. Now, most of us have learned the very simple equation that rate times time equals distance. So if we take the rate and multiply the time. Now, what time do we use? We want to use the time between conjunctions as our time. That's called the synodic period. It's an astronomical name. And it's basically the time between conjunctions. It's the time for one moving object to catch up and meet with another moving object. Okay, in one synodic period, Saturn will go around the orbit. We don't know how far, but let's call it d degrees. In the same time, Jupiter is going to go around its orbit once and get back to where it was. But in the meantime, Saturn has moved some degrees ahead of it, and it's got to now move the d degrees to catch up to Saturn. So Jupiter moves 360 plus d degrees, while Saturn moves d degrees in one synodic period t. So if we have the rate for Jupiter times one synodic period, or the time of one synodic period in years, that's 360 plus d. And if we have the rate of Saturn times one synodic period, that equals d years. So we have two equations with two unknowns in t and d. And in 8th grade, most of us learned how to solve two simultaneous equations and two unknowns. And if you do that, you can find t and d. T comes out to be 19.8 years. And d, the number of degrees, is 240. That's 2/3 of the way around the orbit. So between conjunctions, Jupiter moves one time around the sun plus 240 degrees, roughly, and Saturn moves 240 degrees, and it takes about 19.9 years. Now, the question is that a good estimate? We've made a lot of assumptions. Well, I went to the trouble of computing the time between the 2000 and the 2020 conjunction, the 2020 to the 2040, the 2040 to the 2060, and the 2060 to the 2080. For those four conjunctions, the smallest time interval was 19.4 years, and the longest was 20.6. And if you average the four, you get 19.9, which is exactly the number we computed on the back of the envelope. So it's a very good estimate, apparently. So astronomers and other scientists like to do that sort of thing to find an easy answer when the real answer can be very complicated. Neat trick. Okay, I think we've talked a fair bit about this event, but as we've said, this one is 6.2 arc minutes, or a fifth of the full moon, and the event is 30 degrees from the sun, and that's why as the sun sets and these two objects set after it, you don't have much time before they both set after the sun. So you have to see this in the early evening. I point out that after the minimum tonight, they will stay at least one lunar diameter until the 26th of December. So even if you don't make it outside till Christmas night or even the day after, they'll still be within one lunar diameter of each other. So you still get a reasonably good view of the conjunction. Now, Jupiter and Saturn are bright enough to see in the daytime with a telescope. In fact, I looked at them through a telescope this afternoon. The problem is you can't see them by eye, and the only way to point a telescope at it is to have a telescope that's controlled with a very clever computer that can compute where in the sky these objects are, point the telescope at it, and you look in the telescope and you go, oh, there they are. So you couldn't find them by eye. I note, for instance, this Venus, if you know where to look, you can see it in the daytime, but Jupiter and Saturn are much harder. So you might manage Jupiter, but you certainly couldn't see Saturn. Okay, Joe's talked about previous events. The last one this close, as she said, was in 1623, where the two planets were only 13 degrees from the sun. That's hard even with a telescope, even a computer-controlled telescope. And in 1623, the telescope had been invented only 10 or 12 years earlier, and there were very few of them that were computer-controlled. So that was a hard thing to do. And as Joe said, the one before that was in 1226, which was 40 degrees from the sun and only 2.4 degrees arc minutes apart, or a third of the distance this one's apart. That's very impressive. Oh, I had one more fact here. This one is the eighth closest to the sun in the years 0 to 3000. So in a 3,000 year period, this one is the eighth closest, which is not bad. I mean, considering they're every 20 years. Just for grins, in case you're curious, the Great Conjunction of 372 was the closest in the first 3 millennia of this period we're in now, the year 0 to the year 3000. And that one was only 1.9 arc minutes, or about a fourth of the one we've got now. If you're still around, the one in 2040, while it's not a particularly good one, it's going to come out on Halloween. So this was the solstice event. The one in 2040 will be the Halloween event. The next very close Great Conjunction, I think Joe's mentioned this, will be in 2080, almost the same distance as this one, at 43 degrees from the sun, a little better than this. And there's a 4-century cycle because of this rotation of 240 degrees with each event. And after you get a couple of close ones, it'll be 2417 before we start another series of close ones again. The reason, and Joe's sort of mentioned this a little bit, is that if you have two circles on a sphere, they intersect in one point and they're as far apart as they're tipped from one another. So as she said, the largest separation occurs when the two circles are furthest apart, but they can be zero. And that's the time, if it happens to be there, that's when you can get these very rare events where Jupiter actually passes in front of Saturn, the last one being in 6,000 something BC and the next one being in 7,500. And Jupiter can actually cover Saturn and it'll disappear for a little while, a few minutes probably. And I think I will leave it at that.
Okay, thanks, Larry. Yep, and we're fortunate now to have this really close one. Yeah, 372. Yeah, that was a good year. I remember that one, and look forward to some of the ones coming up. Right. Okay, so now we are. You were just mentioning some of the things that Joe's Schindler had been pointing out, and we are going to go back to her for a very quick recap. I know that people come in and out of the stream as we're broadcasting, so we're going to go briefly back to Joe's for a quick recap of the general circumstances of what's going on tonight.
Yeah, hi, thanks, Jeff. Let me go ahead and get my thing showing up for you guys again so you guys can see it. There we go. I'm in the middle of the presentation on here, unfortunately. But yeah, so I'm going to recap what's going on with this conjunction. I am trying to follow the chat pretty closely there. Sorry, I am trying to follow the chat a little bit closely there, but it is pretty quick to try to keep up with. So I am seeing a lot of questions about when they can see it. If it's going to be something that they're going to miss really quickly, how they're going to be able to see it from where they're at. And I'm also seeing a lot of people just really bummed because it's cloudy. So I'm going to lift your spirits a little bit. Even if it's cloudy for you right now, don't worry about it because you can probably go out tomorrow and you can see the conjunction tomorrow. Today just happens to be the closest distance that Saturn and Jupiter are going to have with each other during this time. So if you want to watch the conjunction, what you're going to do is you're going to go outside about an hour after sunset is probably the best time. Anywhere between sunset and about an hour and a half after sunset is going to be when you're going to be able to see them with your naked eye. And you will see Jupiter and Saturn in the southwest sky about a fist's width up from the horizon. So it's still pretty close to the horizon. As time goes on, Jupiter and Saturn are getting closer and closer to the sun and getting more and more difficult to see. Today, they're so close to each other that they do kind of look like one single star together. If you were to look at it with a telescope, you will be able to see the separation between Jupiter and Saturn. But this isn't an instantaneous thing. I've been watching them get closer to each other over the past few weeks now, past couple weeks, and they're going to be hanging around each other for quite a while. So you're not going to miss the conjunction. If you blink it and you miss it, that's not going to happen for us. So if it is cloudy for you right now or raining, like I heard it's raining in Seattle, then you can go out tomorrow and they won't be much farther apart than they are today. So you will be able to see them all the way up until probably the end of the year. And by then they're going to get too close to the sun that it's going to be just difficult to see without, looking directly at the sun at that point. So this is what the horizon looks like where I'm at in Flagstaff. And your sunset is going to vary based off of your latitude, but you should get a similar view to this no matter where you are. And of course, if you're in the southern hemisphere, you're going to look north instead of south so you can see the sunset that way. I do have a little bit of a video right here so you guys can see over the past month how Saturn and Jupiter have moved. So every little click is one day. And then here we have today right here, and they're going to start getting farther apart. I realized I pointed with my finger and not with my mouse, so you guys didn't see that. But it is something that's not going to happen instantaneously. It does take some time to do. And just like you can see in the feed, you can see Jupiter and Saturn on the screen, and I'm not too sure which image you're getting right now, but you will be seeing them. They'll look still like this. They're not moving so quickly from our perspective that they're going to zoom by each other. And just to reiterate, Jupiter will not be eclipsing Saturn. It's not going to be passing in front of Saturn at all this millennium. You'll have to wait until about 7000 AD to be able to see Jupiter eclipse Saturn. So this is as close as they're going to get, is about a fifth the width of your pinky at arm's length. And the reason that this is happening at all is as Jupiter and Saturn go around the sun, from our perspective, it looks like Jupiter is passing Saturn by. But in reality, Jupiter is about half the distance to the sun as Saturn is. Saturn's about twice as far away, which means Jupiter and Saturn, they will not be colliding. Jupiter's about 500 million miles out, and Saturn's about 1 billion miles out. So there's no way that they're going to run into each other or really do much to affect each other at all. It just happens to be, from our line of sight, they look like they're lining up. It's a matter of perspective. And then these conjunctions, they happen every 20 years, although you've probably been seeing, oh, this is a once in a 400-year event. They do happen every 20 years or so. So there will be another great conjunction in 2040 and in 2060. But the next best one that is as good as this one, where they're as close as they are, that's going to happen in the year 2080. So, and then of course, this was the last time that we saw them this close was about 400 years ago. But we do see great conjunctions happen every 20 years. So that's sort of my quick version. I hope I answered a lot of questions that I've been seeing in the chat there. And I want to thank you guys, and I'm going to turn it back over to Jeff.
Okay, thanks, Jose. Thanks for recapping what's going on there. And yeah, again, everybody's joining in and out of the chat of the feed as we go along. So just as a reminder, you can see this as two stars. I saw comment go by in the chat that somebody saw 2 dots in LA, one brighter than the other. In the southwestern sky, that's almost certainly it, the fainter one of the two being Saturn. So it does not appear as a single star. As we've noted, the 2 planets are about 6 arc minutes apart, and your eye can resolve down to about 1. So you'll see these as 2 distinct dots at their closest approach tonight. So what we've got on the feed for you right now, this is a live view from a telescope near the Lowell Discovery Telescope. Our electrical engineer Mike Collins is out there collecting this view for you. You can see Jupiter toward the bottom of the screen and Saturn near the top, much fainter, and that's because this is a live view, and Saturn actually is quite a bit fainter than Jupiter. If you go outside and look at this phenomenon in the sky, you'll clearly see that Saturn appears quite a bit dimmer, even to your eye. It's great to see so many people from around the world. Say hi to our friends at Mexico City. I guess it's cloudy in Mexico City. Sao Paulo, Brazil, hello. And the Philippines, where it must be about midday on the 22nd at this point. Great to have some folks joining us all the way from the Philippines, coming all the way back here to Flagstaff, Arizona, where it is now about 6:30 p.m. So for the rest of the live stream, we're going to be showing you this live view from the Lowell Discovery Telescope. The planets are now too low. They're down in the trees for us to be able to see from the Giovanni Open Deck Observatory here on campus. But that is a live view. Again, you can see the planets moving around just a little bit because they're getting quite low in the western sky, and we're looking through a lot of atmosphere. And the more atmosphere you look through, the more turbulence you get, the more twinkle you get. You know, if you're an astronomer trying to get really good observations, you don't like twinkle. The less twinkle, the better off you are. So that's where we are right now. Now, we've been talking about these 2 giant planets in our solar system, and they're really cool moons. What we're going to do now is bring our astronomer, Dr. Joe Lama, on. And Joe is an expert in planetary systems, except around other stars. And we were talking about how cool the technology is these days that we can build a drone to fly around Titan. It's also pretty darn cool that we can characterize and observe planets around stars literally trillions of miles away. So, Joe, you're calling in from a unique venue out there.
Thanks, Jeff. Yes, I'm here on location at the Lowell Discovery Telescope. So behind me here, you can see our recoating chamber for our 4.3 meter telescope. So I'm out here making sure our live feed is working. And I'm also going to talk to you now about some of my research here at Lowell, where I search for and characterize exoplanets. All right. So yeah, my job here at Lowell is to go out at night and use our 4.3 meter telescope to try and find exoplanets. And so exoplanets are just planets that orbit stars other than our sun. And so you can see here this beautiful image of the Milky Way. And here you can see thousands and thousands of stars, billions of stars in our Milky Way. And each one of those is a solar system just like our own. And in the last 20 years or so, we've learned that these stars likely all host planets. And so my job is to go and find those planets. And so you might ask, how do you go about finding an exoplanet? And so the analogy I like to give is that we are searching for the light coming from a firefly that's orbiting around a lighthouse. So here you can see the lighthouse is very bright, it's shining. What we're trying to do is find this light from a firefly that's right there. And so it's a really challenging job. And that's why the technology advancements in the past, 20, 25 years have really enabled us to do this and find exoplanets. And so one of the ways that we actually find exoplanets is by direct imaging them. And so here you can see on the right-hand side, you can see an image of a star that's very speckly. We've zoomed very far in on this. And what astronomers do is they create what we call a coronagraph, where they try and block some of the star's light out to reveal the presence of an orbiting planet. Now here on the left, I'm showing the most famous system that has been observed through this method. This is the HR 8799 system. And here you can see a few years worth of data, and you can see the central star in the middle being masked out, and you can see these planets all orbiting around the star. And so this is one of our first multi-planet exoplanet systems. And so that's going to be the focus of this talk, is on not only finding exoplanets, but finding multi-planet systems where conjunctions could potentially happen. So direct imaging is a very powerful technique. It's yielded a few systems. It's very observationally expensive to do. But my research here at Lowell, we actually use a different technique. We search for the radial velocity motion of a planet orbiting its star. And so having a planet like Jupiter in our solar system actually causes the center of mass of the system to move. And so not only do the planets orbit the star, but the star actually slightly wobbles under the reflex motion of the planets in the system. And so you can see here an animation showing this. You can see as the planet orbits, the star also slightly moves as well. It moves towards us and away from us with the same orbit, with the same period as the planet's orbit. And the amplitude of the modulation tells us something about the size of the planet. And this is a really powerful technique. This technique has been used to find over 700 exoplanets. Again, it's quite computationally expensive, but it is very powerful and enables us to actually measure the mass of an exoplanet, something I'm very interested in with my research. And so here at Lowell, I'm sitting in our recoating chamber for the Lowell Discovery Telescope. It's a 4.3 meter telescope. And so in collaboration with Yale University, we actually built a new instrument that's one of the best in the world for finding these exoplanets, for measuring the Doppler motion, this tiny wobble of a star in the presence of a planet. And so here is the instrument. We call it Express. It's the Extreme Precision Spectrograph, built by Yale University and installed on our 4.3 meter Lowell Discovery Telescope. And as I say, it's one of the most advanced instruments for finding exoplanets. It uses state-of-the-art technology, including, next generation fiber optic technology, new CCD cameras. And we actually use what's really cool. We use a laser frequency cone for wavelength calibration. You can check out many talks on the Lowell Observatory YouTube channel where we talk about Express. Indeed, one of my main projects has actually been observing with Express during the day of the sun. And so what's really cool about Express is it's capable of measuring the radial motion of stars down to about 30 centimeters per second. And when you think about that, that actually turns out to be about the same speed as the world's fastest tortoise. This is Bertie. And so when he goes full pelt, can go about 20 to 30 centimeters a second. But if you think about it, we're measuring a star that's, many, many light years away, moving by this tiny, tiny amount. It's really, really incredible. And you need that precision to actually go and detect small planets like that, like our Earth. So when we're looking for planets like the Earth in the habitable zone of a star like our sun, you need to be able to measure this really small technique. And we're now with instruments like Express on the LDT, we're on this verge of being able to do that. So it's a really exciting time to be an exoplanet astronomer. So radial velocity methods have found about 700 planets, but the real workhorse for finding planets is actually transits. And something very similar happens with a transit as with a conjunction. So from our viewpoint on Earth, what we do is we measure the brightness of a star, and we look for a periodic dip in the star's light as a planet moves between our viewpoint of the star and the star itself. And we call that event a transit. Now, a transit is very powerful because the size of the dip tells us how big the planet is. Jupiter around a star like our sun gives about a 1% dip in light. A planet like Earth is just a 0.01% dip in light. And so you have to make really precise measurements. So in 2009, NASA launched the Kepler spacecraft, whose sole mission was to monitor the brightness of thousands of stars to search for these tiny dips in light caused by orbiting planets. And it did incredibly well. It found many, many thousands of planets and planetary candidates. And now we use instruments like Express on the LDT to try and measure the masses of these potential planet candidates. Now, NASA's latest spacecraft is the TESS mission. It's the Transiting Exoplanet Survey Satellite. Now, TESS is really cool. So it observes a quadrant of the sky. You can see it here for about 20 to 30 days at a time. Then it rotates, moves on, does another one, and keeps going. And then it flips after about a year and then does the same thing again. And so it's an all-sky survey. And so we're mapping out the whole sky, monitoring thousands and thousands of stars to search for exoplanets. And we found a lot of really interesting ones. These are some of my favorite ones. These are from the NASA Exoplanet Travel Bureau. So, you know, if you're really feeling adventurous, you could go and experience the Super Earth HD 40307G. If you went skydiving there, it would be pretty entertaining. Kepler 186f is another one of my favorite systems, where the star is much smaller than our sun, and so it actually emits light in a much redder wavelength. And so likely grass on those planets would be a different color to grass here on Earth. So I think that's very cool. This movie really shows sort of how the state of exoplanet science. And so here you're seeing the dashed circles are the planets in our solar system. Then each one of these other star systems here shows the planets color-coded by their temperature and size to scale within our solar system. And so you can see there are thousands and thousands of these systems that we found with many, many planets each. But what you can see is that they're all much closer to their parent star than, say, we are to the Earth. And so the Earth is here to scale. So you can see all these systems have planets that are much closer to their stars than we are to the sun. Now, one of my favorite exoplanet systems is actually the Trappist-1 system. This was a system discovered in 2017, and it's really special and I think rather relevant to today's topic. This is a star that's about a tenth the size of our sun, so barely larger than Jupiter, but it actually hosts 7 Earth-sized exoplanets, and you can see them all whizzing around here. And what's really cool is because this system, the star itself, is so much smaller than our sun, the actual habitable zone where a planet could have the right temperature for liquid water to exist is much closer to its star. And so here you see the 7 planets in the Trappist-1 system. You've got Trappist-1b here, the closest one in. This has a 1.8-day orbital period. And the temperature is very hot, as you would expect. But if you go out, planets E, F, and G are potentially in the habitable zone of this star, even though their orbital period is just of order 10 days. It's much smaller, they're much closer into their star than we are to our sun. And so here's just a size comparison showing you our sun with some sunspots here on the left next to the Trappist-1 system. And if you were to put Jupiter on this plot, it would be basically the same size as the Trappist-1 star. It's a really cool system. And that's, as I said, having the star itself be much smaller means that the habitable zone where liquid water can exist is much closer. And so this movie just highlights that really nicely. In the center here, you have our solar system, and then you have hotter stars above it and cooler stars below it. And the green area here to scale is where the habitable zone would be. So for the cool stars like Trappist-1, it's much closer in. And so just to highlight this system again, because I think it's a really interesting system, you can see our solar system here at the bottom. And to scale with those lines going in is the entire Trappist-1 system. So you've got these 7 planets really, really close to their parent star. And so conjunctions actually happen on almost a daily basis on this system. Here you've got the innermost circle here going around is Trappist-1b with a 1.8-day period. And on the outer, the blue one here is Trappist-1g, which has an orbital period of, I think, about 12 to 18 days. And so you can see every time some of these line up, that will be a conjunction, just like we're having tonight in our solar system. And so you can see here, this is a really cool artist's rendition of what the view on Trappist-1e would look like. And so you would be able to make out these planets in this system. And so I will, and I will just conclude there and say that, exoplanets are a really exciting field to be working on right now. And we're hoping to find many, many more of these multi-planet systems as time goes on, where conjunctions are all but a regular occurrence.
Okay, thanks, Joe. Yeah, definitely with everything packed in like that, conjunctions are going to happen all the time. And
exactly.
As noted at the start of the stream, look, one of the central components of Lowell Observatory's mission is astronomical discovery. Joe and Jennifer, Michael are all members of our research faculty here at the observatory, and it's great to have a tool like the Lowell Discovery Telescope and the Express Spectrograph to make these observations possible. So thanks a lot, Joe. So to update where we are now, it is 6:45 p.m. here in Arizona. To the left of me on your screen, you can see a live view of the Great Conjunction from a telescope near the Lowell Discovery Telescope. We can't observe it from the Giovanni Open Deck Observatory anymore. The planets have gotten a little bit too low for that. They're down in the trees, but we can still see them from out at the Lowell Discovery Telescope site. You can see Jupiter there at the bottom. Saturn much fainter at the top. The planets are getting quite low. We'll be able to observe them for another 30 to 35 minutes probably. So they're jumping around because you see a lot of atmospheric turbulence that's making the images jump around a little bit. I saw some, while Joe was talking, some quick questions that we can just quickly recap to remind you of how to enjoy this phenomenon. Will the planets get any closer than they are tonight? No, we're broadcasting tonight because this is the closest approach. Several people on the chat asking, so is the conjunction happening? Has it happened yet? It's ongoing. This is a slow unfolding event. While tonight is the closest approach, as Joe Schindler pointed out in a previous segment, over the next couple of weeks, you can go out and look in the southwestern sky and see the planets. They'll gradually be drawing farther apart, but you can still observe this for the next couple of weeks before they get a little too close to the sun to observe it safely. And let's see. And the planets you see in the live view here do not appear to be moving because they're so far away. They are, of course, moving, as Larry Wasserman was talking about, but they're far enough away that we don't see the motion in real time here on the image. So actually that's good because it's apparently cloudy in much of the world tonight. You know, Mexico, the eastern US, Seattle, apparently it's raining over in Germany as well as the UK. This is like a worldwide weather broadcast we're getting here tonight. So if it's not viewable tonight, you have many nights over the next couple of weeks when it's clear to go out and enjoy the sight, because the two planets will still be really close together for quite some time yet. So Joe, if I could, one question came in on the chat that I'd like to fire over to you. You were talking about the neat Trappist-1 system, and there was a question on how many of those do we think might or might not be tidally locked, which means like the moon around the Earth, so always facing the same side. Are you still? Okay, I'll wait. I'll ask that again. We'll see if Joe is back later. Oh, I guess Joe, all right, I got a message on the chat. Joe has gone outside, presumably to look at the beautiful sight in the sky. So if he comes back, we'll drop him a note in the chat and see if we can get an answer to that question. In the meantime, I'm going to say, again, it's great to see still a worldwide audience, but we've gotten hellos. Really, you're still watching in Belgium and Germany, and congratulations, it's getting really late over there. And Mendoza, Argentina, nice to have folks from the Southern Hemisphere. Hope you enjoy the summer that's beginning today. And in Indonesia, so it's probably, again, midday tomorrow over there as well. So one thing that's been picked up in the media recently, of course, this is happening just 4 days before Christmas, a very close conjunction of two bright planets forming not a single star, as we said in the last segment. You can see them apart as two distinct dots, Jupiter brighter, Saturn fainter. But the comparison to the Christmas star and culturally significant events has certainly been made quite reasonably. And so for the next segment of our stream here, we have Lowell Observatory's historian, Kevin Schindler, no relation to Joe's. It's just a statistical fluctuation there, I think. And Kevin is going to talk to us tonight about some of the cultural interpretations of these rather spectacular sights in the night sky. Kevin, take it away.
Thanks, Jeff. And it's great to be part of this live presentation from Lowell Observatory in downtown Flagstaff. We do feel fortunate that we have clear skies here. And that's one of the reasons why Percival Lowell founded this observatory here in 1897, because of the clear skies and a lack of pollution and such. So this is a kind of night where we really celebrate that. I'm going to turn a program on here, get her started. And then we're going to talk a little bit about conjunctions in history. Larry has talked a little bit about this. Joe's did also. I'm going to maybe review just a little bit because our viewership is evolving here some tonight. So I think this is a great event for us because we can talk about the great science and hear from astronomers and planetary scientists and educators on different aspects of what this means scientifically. But I think it's also a neat event because we can tie in culture and religion. And especially this time of year with Christmas, and as Jeff mentioned, the links of this conjunction with the Christmas star. And so I'm going to talk about that a little bit. First of all, we'll just talk about a few historic conjunctions, a couple of things that I think are kind of fun. Now, when I was growing up in Valley City, Ohio, if I heard conjunction, the only thing I would have thought about was the classic Schoolhouse Rock conjunction junction, what's your function? I can still sing that whole song. But I've been at Lowell Observatory for 25 years now. And when we talk about conjunctions here, we're talking about stuff in the sky. And as we've heard earlier, conjunctions are essentially just things bodies up in the sky, astronomical objects that appear to get close to each other. They can be planets, they can be planets and moons, or planets and the moon, they can be stars and moons. We heard earlier from Larry Wasserman, and Larry has spent his career studying these kind of interactions. This picture was taken in 1911 by E.C. Slipher, one of the early and long-standing astronomers here at Lowell Observatory. And it's a picture of the moon on the left and Mars on the right. And again, you get an idea, as we say these things appear close in the sky, of course, they're not really that close. Mars is tens of millions of miles away. The moon's only 250,000 miles away. So put them together in the sky, the moon's going to look a lot bigger. It just is our two-dimensional view that they get close. Now, if the bodies that we're talking about are Jupiter and Saturn, the two largest bodies in our solar system, that's when the term great conjunction comes in. And these great conjunctions happen every 20 years. They're not that uncommon, every 20 years, and they're very predictable. But some are more special than others. And that's why we're doing this program tonight, because as Larry mentioned, since essentially Jesus' birth 3,000 years ago, or a couple thousand years ago, this is in the top 8 of how close they got together. So that's pretty remarkable. And so it's really close, and it's worth looking at, and we'll get to this when we talk about the Star of Bethlehem later, but this is one of those objects that you don't look at and say, wow, that's visually stunning. It is interesting to see them close together, but it's not like, seeing Saturn through the Hubble Space Telescope. But the fact that when you understand what's happening and how infrequently these close approaches happen, then it makes it pretty special, I think. As we heard earlier, we have to go back almost 400 years since we had a conjunction of Jupiter and Saturn where they were this close in the sky. And Galileo himself, shown here, had just invented his telescope a dozen years before this. And in fact, this is a great person to talk about, because as we look at that live feed now from the Discovery, or the Lowell Discovery Telescope facility from a small telescope out there, we're seeing Jupiter and Saturn, but we're also seeing, I think, 3 of the 4 largest moons of Jupiter, the Galilean satellites. And those are named after Galileo, who first saw them when he looked at the skies through his telescope in 1610. So we have to go back that far, but that conjunction, that great conjunction, the planets were near the sun, and so not easy to see. We have to go all the way back to the days of Genghis Khan in 1226, when we get another conjunction that's as close as we have this year. So again, I think that's what makes this so interesting, is that, it's not as stunning maybe visually as some things, but when you realize what's happening and how unusual it is that they get this close, it makes it pretty special. Now, there's another conjunction I'd like to mention that I say kind of in tongue-in-cheek a little bit. In 1841, there was a great conjunction, and remember, they're every 20 years. Well, the president who had been elected just the year before, was William Henry Harrison. And it turns out that starting with William Henry Harrison, every 20 years, there's a great conjunction. So you have William Henry Harrison, James Garfield, William McKinley, Warren G. Harding. I forgot Abraham Lincoln was second in there, FDR and John F. Kennedy. So for that range of time, from 1840 to 1960, every 20 years, there's a great conjunction. And every 20 years, those presidents died in office, which is just almost an eerie thing. And I think those of us who grew up when I did, we remember this. Luckily, that trend stopped after JFK, even though Ronald Reagan, next in line, was shot. He survived it. But I say this because I think it brings up something that we always keep in mind, that you can draw connections to a lot of things, but whether one causes the other is not necessarily the case. And it reminds us of critical thinking and how, there's a lot of things out there. When I was growing up, the joke was, well, it's on TV, it must be true. Today if it's on the internet, it must be true. One of the things we try to do here at Lowell is, do things in a scientific manner and think about things critically. And so in this case, I just mentioned this because, of course, there's no correlation between great conjunctions and the death of those presidents. But it brings up another interesting so-called correlation that was made years ago. A geophysicist named Richard Lindzen, who was studying the sunspots on the sun. And sunspots, they go through 11-year cycles. Every 11 years, there's a lot of activity, then there's not as much. And he correlated from 1965 to 1985 the number of sunspots, and lo and behold, it correlated pretty well with the number of Republicans in the U.S. Senate. So clearly, those two are related. I bring this up just because it's kind of funny how you can draw these similarities. It doesn't mean it's true. So what's that have to do with conjunctions? Well, the reason I bring that up is because, conjunctions were important, especially to ancient people. We talked about how we think about critical thinking, and if just because there's a conjunction, does that have an impact on us on life? Was that the cause of the presidents dying? I think we would all agree no. But looking at the positions of the planets and how they move across the sky was really important, especially to ancient civilizations. They didn't have TV or anything to look at night. They went outside and looked at the sky. And they noticed these bodies moving faster than other ones and called them planets, which means the wanderers. They were wandering against the background sky. And so this brings us to, I think, one of the more fascinating things of this season, and that's the Star of Bethlehem. At this time of year, we see this Star of Bethlehem, or the Christmas star, on cards, on TV shows. It's a really iconic image of this time of year. And, astronomers and others for centuries have tried to figure out, what is this? Was this just a miracle that is beyond the comprehension of us humans? Or was it a real astronomical event of some sort? And so it's kind of a fun opportunity to look at the science and look at the religion and see if we can come up with an understanding of what that Star of Bethlehem might have been. And when we talk about the Star of Bethlehem, we have to remember, this is based on the writings in Matthew in the Bible. And a couple thousand years ago, the term they used for stars, for instance, doesn't necessarily mean the same thing we use it as today. A lot of these things have evolved in time. Just like a meteor, we think a meteor is, as Nick will talk about in a little bit, a piece of debris that's flying through our atmosphere, burning up. But in the old days, meteors also refer to water droplets and pretty much anything in the sky. So when we think about the term star, we have to go beyond just if it was a normal star as we think about it, maybe just something bright in the sky. Because if the star was a regular star, it wouldn't have been special to the wise men. And as we think about this, remember, they were very tuned into the night sky. So the Star of Bethlehem, we see it represented as like a really bright thing, like in this picture. But maybe it wasn't so visually bright, just like the conjunction this year, but maybe it was that it was important to them because the way the planets were arranged. And that's something to keep in mind as we go along. So what was the Star of Bethlehem? One idea was, if it's not a regular star, maybe it was an exploding star, a supernova. And those have been witnessed throughout history periodically. This is the remnants of a supernova captured with the Lowell Discovery Telescope. And certainly this was a possibility. If there's a supernova that somebody viewed, that would be something that stands out. But as it turns out, when we go back to the ancient records, the observers didn't record anything like this in the time that we think Jesus was born. And that's another tricky part of it. We don't know exactly when Jesus was born, probably somewhere between 1 and 7 BC, based on tax records and such text, but we don't know. And so trying to narrow down this event, that makes it difficult. But during that period of time, we think Jesus might have been born. The ancients didn't record any big supernova type events. Well, maybe it was a shooting star like we talked about. And, a big one we call a bolide that makes this really gray streak across the sky. And here's an image of one captured from a camera, a suite of cameras. This is about 12 feet from where Joe is standing right now. This is mounted on top of the building where he was sitting when he gave his program. And it's looking at the sky every night. And Nick is going to talk about this a little bit later on. But probably not a shooting star like we see here, because those just happened. They're gone in a flash of a second. It's not something that the wise men would have been following night after night. So that doesn't seem to make sense. Maybe it was Halley's Comet. Halley's Comet in modern times is a real icon of the night sky. And imagine if Halley's Comet had happened back at that time. You could see this as being a pretty major thing that could maybe represent that star. And in this picture, there's even more you can consider because this big sphere is Venus, the planet Venus. This picture was taken in 1910 of Halley's Comet, taken right up here at Lowell Observatory. And it's a great picture because it not only shows Halley's Comet, it shows Venus, the city lights of Flagstaff in the lower left, and also a meteor shooting through the comet. Well, scholars have looked back, and we know the period of Halley's Comet pretty well, and know that in that frame of time we're looking at, Halley's Comet didn't make an appearance. It was close in something like 12 BC, so perhaps if the number is a little bit off, maybe it could be that, but it doesn't quite fit in. Maybe it's another comet. There are a lot of other comets that have been seen through the years. Earlier this year, we had Comet Neowise. This was taken over the Giovanni Open Deck Observatory, where we viewed the planets earlier. But again, the ancient observers, there was no clear-cut comet that they recorded in that period of time. So what could it have been? And you can see where this is circling around back to the conjunctions. Again, maybe it wasn't a dramatic visual thing, but something that was meaningful because of the way the planets and other things aligned. We can go back in time and we can project when these conjunctions take place. There were, in this time period we're looking at, there was a conjunction of Mars and the moon, like E.C. Slafer photographed. So there are several possibilities during this period of time. But, maybe the wise men were looking up, just like Samantha Gorney, our education deputy director, did just a few nights ago, when she looked up in the sky and she saw the two dots, and the moon happened to be up at that time showing Earth shine, that reflected light. But maybe just like she's doing, they looked up and saw Jupiter and Saturn, this great conjunction, and that's what, not visually stunning, but important to them. And maybe that's what they saw. Because it turns out in 7 BC, or BCE, before Christian era, there was one of these great conjunctions. And this one was special because it was a triple conjunction. And that means, Larry introduced this idea before, you know, we think about the planets, we're all on racetracks. Like Earth is on the inner lane, Jupiter is on an outer lane, Saturn is even further out. There's all these things that are spinning around. Sometimes the planets seem to pass each other, go backwards and pass each other again. And such is called a triple conjunction, and this happened in 7 BC. So perhaps this is what the Star of Bethlehem was. And we don't know, we'll probably never know if it was this conjunction or one of the other ones that occurred during that time. But I think it's a fun thing to talk about, and again, to connect that science with the culture, and especially for this time of year. So that's a little introduction to the culture of the Star of Bethlehem and why so many media outlets have been calling it the Christmas star.
Okay, thanks a lot, Kevin. That always interesting talk. And thanks everybody for staying with us as our coverage of the Great Conjunction continues. So what we're showing on the screen right now, we have an image up here of the conjunction taken yesterday from the Lowell Discovery Telescope, and now we're switching to the current live view. So you can see Jupiter there a little bit farther towards the bottom, and Saturn up near the top. I did see a question go by quickly in the chat asking about the planets jumping around, and we've mentioned that before. They're getting very low in the west. We're going to be able to observe them for about 20 to 25 more minutes, which is about the time we're planning to wrap up the live stream here because the planets will set. Some questions in the chat of, you know, when the conjunction is going to happen. It's happening ongoing. Right now, today is when the planets appear closest together. So this is sort of the peak of the conjunction, the maximum point of it. But fortunately, you know, if they've already set where you're living, or if it's cloudy, as a lot of the world seems to be tonight, you'll be able to see this in the western horizon, sort of southwestern sky during twilight, dusk, sunset, the couple hours immediately right after sunset. Doesn't particularly matter where you are. You don't have to be in Arizona or anywhere else, just shortly after sunset for the next couple of weeks before the planets start to get a little bit too close to the sun to observe safely. So that's what's happening right now. This is a very common phenomenon as we observe objects that are lower in the atmosphere. The observing gets steadily worse and worse. And in fact, for research observations, we would rather infrequently be observing objects this low in the sky because of all the atmospheric disruption and turbulence. So what we're going to do for the last segment of our live stream here before the planet set, as you've seen, if you've been watching the whole time, there are a lot of things going on in the sky. You know, Jupiter and Saturn are kind of the stars of this particular show, but they have all these interesting moons that Jennifer talked about. Joe Lama talked about all the planets we're finding around other stars and how those systems can have conjunctions as well. Joe did come back and answered that question that came on the feed a while ago. So if the questioner is still there, we think probably most of the planets in the Trappist system are tidally locked, probably because they're just so close to their star. That tends to be fairly typical for objects close in to the object they're orbiting. And we've seen all of the cultural aspects of this from Michael and Kevin, and of course the specific circumstances of the geometry of what's going on tonight from Joseph and Larry. So to wrap up tonight, there's another thing going on tonight that maybe hasn't captured the limelight because of all the hype on the conjunction, but that is an ongoing meteor shower, the Ursid meteor shower. There are a number of meteor showers throughout the year. If you go to Lowell's YouTube stream, YouTube channel, you can see we generally do coverage of a lot of these, most recently the Geminids, of course the Perseids. And so we, as we have experts in so many areas of astronomy, we have an expert on small bodies in the solar system, so asteroids and meteors and the like, and that is our astronomer Nick Moskowitz, who's with us tonight. And he's going to talk to us a little bit about this meteor shower. So if you go out to look at the conjunction, maybe you'll get the bonus of a few meteors. So I'll pass it off to Nick.
All right, thank you, Jeff.
So this is sort of a talk that will be now for something completely different. I'm not going to be talking too much about the conjunction this evening, but instead, as Jeff said, there's actually a meteor shower tonight that is potentially going to be quite an interesting one to stay up for. So if you're out watching the conjunction and want something else to stay up for, tonight is the predicted peak of the Ursid meteor shower, which is perhaps one of the lesser known meteor showers, but it is an annual meteor shower. And as I'll talk about here, it has the potential to do what we call outburst tonight, which would be very exciting. Outbursting meteor showers produce a lot of meteors over a short period of time and can really put on quite a celestial show. So in this talk, I'll talk a little bit about what are meteor showers, what produces them, and I'll talk specifically about the Ursid meteor shower tonight. Talk briefly about some of the research that we do here at Lowell related to meteors, and then I'll finish with some viewing tips. So again, if you're interested in going out tonight to catch some meteors, I'll give you some tips on where to go and how best to see them. So to start off, we need to go over a little bit of terminology here. Oops. Okay, there we go. So going over some terminology here of meteors and what it is we're going to be discussing in this particular presentation. Meteors are just part of sort of the collection of small planetary bodies that we have in the solar system. And that ranges from comets and asteroids, which are chunks of sort of leftover planetary material that are whizzing around the solar system, just like the planets are circling the sun on their orbits. These asteroids and comets are relic pieces of debris that circle the sun, and we study them to learn about processes in the solar system, as these things are more or less left over from the time of planet formation. So they've been largely untouched for the past 4.5 billion years. And that tells us a lot about not only what the conditions were like when the planets formed, but also what has happened in the solar system since that time. Now, pieces of comets and asteroids can get blasted off their surface through a variety of processes, and I'm not going to get into that too much. But when those small pieces get removed from the surface of an asteroid or a comet, they can be referred to as meteoroids. And a meteoroid is really just a fragment of debris or debris from an asteroid or comet right before it's about to hit the Earth's atmosphere. So it's sort of a proto-meteor or a meteoroid. Now, when that meteoroid enters through the atmosphere, it can burn up in the atmosphere because it hits with such extraordinary velocity. Typical meteor velocity may be many tens of thousands of miles per hour, which is pretty extraordinary to think about. And so that meteoroid just vaporizes essentially on impact with the Earth's atmosphere and appears as a bright flash of light. And that flash of light is what we call a meteor or a shooting star. The vast majority of meteors that we see are actually quite small little meteoroids. They're no bigger than, say, a grain of sand or a pea-sized piece of rock that's coming in and hitting the atmosphere and, again, vaporizing when they come into contact with the atmosphere. Those events are relatively common throughout the year. Meteors show up all the time. But on special dates, and tonight is one of those, we get what are called meteor showers. And that's when a whole bunch of meteors appear at once, appearing all to originate from a single point in the night sky. And we'll talk about the Ursid meteors here in just a second. If that meteoroid is big enough to survive passage through the atmosphere, that violent process in which material is being vaporized as the meteor burns up, if it survives all the way to the ground, we refer to those things as meteorites. Those are the pieces of sort of space debris that land on the surface, and we can go collect and pick them up and study them in a laboratory. So that's the sort of terminology I'll be using when I'm referring to this, and we're going to be focusing mostly on sort of meteors and meteor shower type of terminology here tonight. Let's see. So I'm having a bit of technical difficulty here, and so I'm going to restart the presentation. I may have to do this for each slide. I'm not entirely sure why. I apologize for this. So tonight is the Ursid meteor shower. And that meteor shower is caused by a well-known comet, comet 8P Tuttle. We see here an image in the upper right-hand corner of Comet Tuttle and a sort of diagram like we've been seeing all night in the bottom here, where this is sort of a bird's eye view of the solar system. We have the gas giant and ice giant planets as the outer rings, Jupiter, Saturn, Uranus, and Neptune. And then the small rings in the center of this diagram are the terrestrial planets. And we can see the orbit here of Comet 8P Tuttle. Comet 8P Tuttle has an orbit period of about 14 years. It has an orbit inclination, sort of inclined relative to the plane of the solar system by about 50 degrees. Eccentricity, so its orbit is highly elongated with the eccentricity of 0.8. And the nucleus of this comet is about 4 kilometers in size. And it's actually a contact binary, which is really interesting morphology, where you have 2 chunks of planetary-like bodies stuck together. So when 8P Tuttle orbits around the sun every 13, 14 years, when it comes in close to the sun heats the comet up, and that causes ices and gases on the surface to be ejected or to escape due to that heating. And that can create a coma of material around the comet, like you see in the image here, and a dust trail. That doesn't show up terribly well in this image, but essentially the heating of these cometary bodies when they come in close to the sun produces lots of debris and material coming off of the nucleus of the comet. And that's exactly what 8P Tuttle has been doing for millennia. Every 14 years or so, it comes into the inner solar system, heats up, releases a bunch of material, and then goes out past the orbit of Uranus, or at least into the outer parts of the solar system, and cools down and stops being active until it makes its next passage into the inner solar system 14 years later. But when that comet does that, it releases a lot of material, and that material over time will populate essentially the orbit of that comet. So you have lots of little pieces of cometary fragments that live in that orbit around the sun, and it's the same orbit that the comet follows. Now that particle stream that Comet 8P has left behind actually intersects the orbit of the Earth. So we have a stream of particles from the comet, and we have the Earth going around the sun, and the Earth can pass through that stream of particles. And that stream of particles is roughly fixed in the solar system. So every year, as the Earth is going around the sun, it passes through that stream of particles. And that is what we see as the Ursid meteor shower. It's this annual meteor shower of us passing through the debris field left behind by Comet 8P. And we see it every year. But the intensity of that shower can vary dramatically. The intensity depends on where Comet 8P is in its orbit, in its 14-year orbit around the sun, and where the various streams are that 8P releases every time it comes in, every 14 years that it comes into the sun. So every 14 years, 8P comes in and releases a bunch of material, and then the next 14 years and so on and so forth. And those streams are not all connected. They move around in space, being perturbed by the planets and solar radiation pressure and things like that. And so the Ursid meteor shower intensity depends on which particular stream we pass through, and again, where 8P is in its orbit relative to its closest passage to the sun. So what can we expect for tonight? The Ursid meteor shower is, as I say, not necessarily one of the best known meteor showers. This is a plot showing the rate of meteors over the course of the year from January through the end of the year. And we see some of the well-known and intense meteor showers like the Perseids in summer and Geminids just a week or so ago. And those produce some of the highest meteor rates that we see of any shower. And the Ursids are down at the end of the year here, a small little peak here, sort of at the end of December. You are here. We're at the end of the year, and we expect tonight to be the peak of the Ursids. And the nominal rate for the Ursids is something like 5 to 10 meteors per hour. So it's not a terribly dramatic shower on average.
However, every now and then, the Urshids actually outburst. And as I said at the beginning, an outburst is when you see a lot more meteors all at once. And it's possible we could get an outburst this year. Models suggest it's possible. We don't know. And that's one of the exciting things about meteor showers is it's sometimes a guessing game and you never really know what you're going to get. But it's possible we'll get an outburst because as Comet 8P came in close to the sun in the years 815 and 829, it released a lot of material. And we're going to be passing directly through those two dust streams released 14 years apart back in AD 800, the AD 800s. So if we're passing directly through some of those old dust trails, we may actually get an outburst of meteors tonight, more so than the sort of typical average Urshid meteor shower. Now, what that outburst could be, we don't really know. These are really hard things to predict, but it could be as high as 100 meteors per hour, so sort of 10 times the nominal rate, which would be pretty exciting and would put it on par with some of the most active meteor showers that we observe throughout the year. So again, we don't know. We'll find out. So if you're interested in going out and observing tonight, I'll tell you at the end what time is going to be best to go check out some Urshid meteors. The window in which this outburst could happen is actually pretty narrow, so it really is just tonight. It's unlike the conjunction where you can go out many over the next several weeks and be able to see the conjunction. The Urshids tonight is your one opportunity. It's a fairly narrow peak to this shower. I want to talk briefly about how we're going to be observing it here at Lowell, and then I'll talk about viewing tips if you do want to go out later tonight. So one of the projects that I'm involved with here at Lowell is a project we refer to as LOCAMS, which stands for the Lowell Observatory Cameras for All Sky Meteor Surveillance. And this is essentially a set of video cameras like you see over on the right here. It's a low-cost system that's designed to automatically record meteors in the night sky. This is leveraging off-the-shelf security camera technology, and it's using low-cost board computers. We're using a stack of Raspberry Pi computers to control these cameras. We can see the array of cameras here in front of the Giovanni Open Deck Observatory, which is where we were broadcasting images of Jupiter and Saturn earlier. And these cameras automatically record meteors every night. They follow the approach of other systems that have been developed in various places, the CAMS network, and you can find out more information at this link, or the Global Meteor Network as another example that we're borrowing heritage from to be able to operate a system like this. And the amazing thing about a system like this is it can be incredibly productive. And so here's a snapshot from one of our cameras from a week ago. This was cherry-picked as the peak of the Geminid shower. And on that night, for this one camera, we got 490 meteors for just that one night, which is kind of amazing that, these simple security cameras, off-the-shelf things that you could, buy online can actually produce such a vast number of detections of meteors. And so what you're looking at here is a stack of all the detections from that night. The faint linear features in the background of this image are stars, and every streak in this image is something that our cameras picked up as moving in the night sky. And the vast majority of these are meteors, and in fact are Geminid meteors, because this is the night of the peak of the Geminids. But we do also get other things in here. So there are satellite and plane trails in this image. The cameras are really good at picking up these sort of streaks of light through the night sky. And then, as I said, this is just one camera. We've got a dozen cameras operating now, and we're planning to expand this network of cameras to potentially reach many dozens of cameras throughout Arizona and the Southwest. So we're going to be generating a lot of observations of meteors, and that's going to be enable us to do a lot of really interesting things in terms of understanding where meteors are coming from in the solar system and what their relationship is to their parent comets and asteroids out there in the solar system. And one of the really fun things about the project that we're going to be doing here is with all of that data, we are setting it up to be presented in an exhibit that is being developed now. We're working with colleagues at Northern Arizona University in the Advanced Media Lab thanks to funding from the National Science Foundation, we're creating an exhibit that will allow visitors to look at this data stream of meteors and learn about meteors in much more depth than what I'm talking about now. In an interactive touchscreen media wall that will be deployed. We're going to be building 2 of these exhibits. One's going to be at Lowell and one's going to be out at Meteor Crater, just outside of Winslow, Arizona, out east here of Flagstaff. And so come and visit us in 2021. We're expecting the first of these exhibits to hopefully go online around the summer of that time. And it'll be a chance for visitors to come and interact with a live data stream, essentially. People will be able to come in and see what happened in the night sky last night and what kind of meteors were out there, whether it was a shower or, say, a sporadic meteor that may have dropped a meteorite somewhere in the southwest. So my last slide here is some of the viewing tips for tonight to be able to go out and observe the Ursid meteors. We've seen sort of stellarium views of the night sky here. And so this is the view of the north, and this is for Flagstaff tonight at about 2 a.m. And the reason this particular meteor shower is called the Ursids is that the radiant point, or the point in the sky where it looks like all the meteors are coming from, is in the constellation Ursa Minor, or the Little Dipper. So if you're going out tonight and you want to take a look at some Ursid meteors, I would recommend going off and looking off to the north. You don't need to see the horizon, but a nice vantage of the sort of northern half of the sky would be preferred, because that's where the radiant point is, and that's where all the meteors will look like they're originating from. They will be scattered across the sky, but they all sort of will point back to that radiant point. Some tips on the actual viewing. Find a dark site. Dark skies are best for meteor watching. Get comfortable, be patient. You're not going to see one the minute you step outside, but you need to give your eyes some time to adjust to the dark so you actually can catch some of these meteors that could happen tonight. Avoid your cell phone, avoid laptops, avoid screens of any kind. That messes with your the adjustment of your eyes to the dark. And then the best viewing hours are going to be sort of 11 p.m. to dawn, and that's independent of where you are. Wherever you are on Earth, go outside at about 11 p.m. to dawn, and you may get lucky and catch some of these Ursids in the northern hemisphere. I've highlighted 11 p.m. because that's sort of when the predicted outburst could appear, and that is 11 p.m. here in Arizona, so you would have to adjust for your time zone, but as I said, it's a narrow window, and we think that around 11 p.m., maybe midnight tonight, there could be an outburst of Ursid meteors, which would be pretty spectacular, particularly if they hit rates of 100 meteors per hour. And I tell people that the best instrument for observing meteors is your naked eye. There's no need for fancy instruments. Just go outside, get warm, and hopefully enjoy a good show after what we've already observed was a great show with the conjunction. So I'll go ahead and finish there and hand it back over to Jeff.
Okay. Thanks, Nick. Lots of good shows to enjoy every night up there. Always a pleasure to be on the stream and tell you about them. So it is now 7:25 p.m. here in Arizona. You can see the live feed to my left from near the Lowell Discovery Telescope. We've got just a couple of minutes left. You can see the planets are really jumping around now and looking very, very red. And this is a sign that they are getting right down on the western horizon and about to set here in Arizona. So the feed will end there in just a couple of minutes. And this means at least viewing the conjunction for tonight from North America, certainly from the continental United States, from Mexico, is about over for tonight. If you're on the West Coast in California, you're a little bit west of us, so you've still got a little more time before they set. But as noted before, the conjunction will continue. The planets will be getting a little bit further apart, but over the next couple of weeks, you can go out and look in the southwestern sky at night and enjoy this sight. You could use binoculars. You can use just the unaided eye. This is more than bright enough to see, but it's got to be within 1 to 2 hours after sunset, low in the southwest into the early new year. So it's been great having so many of you online with us tonight from literally all over the world. I've lost count of how many countries were represented. We certainly hope you've enjoyed the stream. If you enjoy this kind of thing, you've been seeing at the bottom of our stream, you can support not only the very cool research that people like Nick and Joe and others, other astronomers here at Lowell do, you can support our ability to bring this to all of you by joining Lowell as a member. We have a large membership program and a great newsletter, and or you can simply make an end-of-year donation. We are a nonprofit, and we rely on the support of everyone to keep our mission going and keep bringing excellent science to as many people as we can. So we really appreciate you joining us. If you like, go visit our YouTube channel. We have a whole variety of streams. We have weekly shows that we do from time to time. I host one of them. Our excellent educators like Joe's can be found doing our interactive stargazing and other ones. So just subscribe to our YouTube channel and you can keep up with all of that. And finally, boy, we certainly hope that we are starting to see the end of the light of the tunnel here as the days in the Northern Hemisphere literally begin to brighten. We hope they are also metaphorically starting to brighten. Science has done its thing. The vaccines are getting out there. We will be on our way out of this. We've been shut down here mostly to the public since last March, since the virus hit. We eased into some very small group premium programs in the fall. We hope to be doing more of those by the spring, when hopefully we're all beginning to build immunity and get back to a slightly more normal year. So we certainly hope wherever you are, maybe your travels will bring you to Flagstaff, Arizona at some point, and you can come experience the Giovanni Open Deck Observatory and all the great information from our educators and astronomers, as we love to do every night when we can. Until then, I'll just leave you by saying what we always do. Stay safe, stay healthy. We wish the best for everybody. We'll get out of this miserable situation the world is in and look forward to a much brighter and happier 2021. Until then, thanks so much for joining us tonight. It's really a pleasure to be online talking with all of you and bringing you this information about the conjunction. Keep looking up, keep enjoying science, and we'll see you next time on another feed. Good night.